So starting on chapter 3 about periodic trends, when scientists started to collect lots of data about different elements, they noticed that there tended to be some recurring patterns in not only the physical properties but also the chemical properties. So these four elements here, boron, aluminum, gallium, and indium, they tend to increase their atomic mass as well as the radius as you go from each element. And the scientists noticed that as we increase their atomic number, their density also increased. So density is one of the properties that is periodic on the periodic table. And remember, density is mass over volume. So even though their mass and their volume were both increasing, the density still tended to increase as we go to more heavier elements. So to be periodic means to be exhibiting a pattern, hence the periodic table. I'm actually having a hard time writing because of this software, so pretend that is in that nice little box. As scientists were studying more, they were trying to figure out how they should group the elements that had similar properties. So Mendeleev in 1869 started to consider increasing an order, or to arrange an order of increasing mass. Let's put increasing mass. And as he did that, he noticed that there were sets that had properties that were similar. When he put them in a table format, he tried to put elements with similar properties in the same vertical columns, and then he noticed that there were gaps in the columns, between the columns actually, and that is where they were able to predict some elements that hadn't been discovered yet. So for example, gallium, there was a hole where gallium should have been, and they called it eka aluminum, which means like similar to aluminum. And they predicted, based on where it should have been on the periodic table, that it should have an atomic mass of 89 AMUs, low melting point, a density of 5.9, should take an oxide formula as this metal 2 for every 3 oxygens, and that chloride. And they predicted it really close. The same thing with germanium. It should fall under silicon, and they were able to predict really accurately the trends or the properties of this element. So what ended up happening is, rather than doing them in order of increasing mass, the elements are listed in order of increasing atomic number, and the rows are called periods, while the columns are called groups or family. And this kind of makes sense because when something is in our family or our group, they tend to have a similar property, so similar characteristics. So elements in the same column are going to, i.e. family or group, those are going to be the ones with similar properties. And quantum theory explains how this works. So quantum is not gone, regardless of how you feel about it. But the periodic law predicts the patterns, and quantum theory is going to explain the why. So there's lots of ways that the periodic table is grouped. The first one we're going to talk about is metals, nonmetals, and metalloids. That is one, and we'll talk about that on the next slide. Another one is to talk about main group elements. And those tend to be very predictable based on their position on the periodic table, and we label those with A at the very top, above all the rows and columns. And then our transition elements and transition metals. Those tend to be less predictable. You can get lots of different types of ions from those, and we label those with label B. So here we have our periodic table. So you can see our main group elements, 1A, 2A, and then skipping over here, 3A to 8A. And then here we have our B's, and down here also is B. So transition elements are down in here, and then our inner transition elements, and then we have our main group elements here and here. Those end up being the S block, the P block, and then our transition elements end up being our D block, and our inner being our F block, which we'll get to. We talked about those orbitals, but now we talk about where those blocks are. We also end up having this little staircase here designates the distinction between metals and nonmetals. We call elements on this diagonal metalloids. And then we call everything to the right of it nonmetals. And to the left of it, metals. So you can see there's a lot more metals than nonmetals or metalloids on the periodic table. So we're going to use the quantum stuff we learned about in the last chapter to help us explain what's going on. We know that electrons are in these orbitals, and so we need to figure out how are these electrons configured, what is their arrangement, and how are they placed in these orbitals. So starting with hydrogen has 1 electron. So the most stable form for hydrogen to be in is in the n equals 1, and being the s orbital. Remember, the s orbital has the lowest energy. And then we will label the number of electrons right here. So that 1 is the number of electrons in the orbitals. And then the 1 equals the energy level, so that would be N. And then our S will be, that's our quantum level number, L. And so how we would write that in an orbital diagram, this shows what it looks like. So here's our 1s orbital, and we would draw a spin up. And that spin up is indicating our 1/2 spin, right? Our spin equals positive 1/2. So this would give us where our electron would be in its lowest energy orbital. But unfortunately, I guess, there are many more types of elements that are way more complicated, so we can't solve them. But we end up making some nice approximations. And these show that many elements can actually act like, or very similar to hydrogen. We also need to think about in multi-electron elements, we're going to have that ms quantum number, and we'll have some splitting of our sublevels. So let's talk about that. So spin is which way, or the orientation that the electron is moving in. And remember, they have the same amount, that half value, but we'll need to be talking about whether it is the direction it's spinning, so spinning up, which means positive 1/2, or spinning down being negative 1/2. So we use that orbital diagram like I showed earlier to show the way. So what we wanted, so again, we'll arrow up, arrow down, spin down. We are going to need the arrows or the spins to cancel in an orbital. And this means that they are paired. Our electrons have been paired. So we're never going to have electrons being the same spin in any given orbital, which means that no electrons will have the same set of quantum numbers. That is one of the ways that we can state the Pauli exclusion principle. I'm just going to write that right here, Pauli. Okay, so if I have something like helium, now helium has 2 electrons, so it's going to be in the energy level 1, both electrons. It's also going to be in the s shell, because the only possible value for n equals 1 is an L of 0. There's only one value for the magnetic quantum number. And so to distinguish our electrons from each other, one will have an m sub s value of positive 1/2, and one will have a negative 1/2. So how we would write that electron configuration is 1s2, meaning that there are 2 electrons from helium, which is true, it only has two. And both of them are in the 1s orbital. And how we would draw them visually in our S1s, we'd have one up and one down, and that would indicate that they have different spins, so different quantum numbers. When we start to get more complicated elements, we're going to have to consider what's happening with the energy of those sublevels. So basically, if I have n equals 3, well, what's happening with the 3s versus the 3p versus the 3d? And so, just as a base definition, if we have orbitals in the same energy level, we would say they are degenerate. When we have multiple electrons in an atom, these energy levels, these sublevels actually split, and that has to do with our electrons interacting with each other, and then shielding and penetration, which we'll get into next time. And so the lower values of L quantum number, so s and p orbitals, tend to have lower energy, which we talked about earlier. So an s orbital has lower energy than a p orbital, which has lower than a d and an f. And so you'll see that here we have our 2s, and then our 2p has higher energy. 3s is lower than 3p, than 3d. 4s, 4p, 4d, and then 4f would be even up higher. And then the Aufbau principle says that electrons are going to fill these orbitals from the lowest energy to the highest. So they'll start with 1s, then they'll go up to 2s, then 2p, 3s, 3p. Notice 4s is actually below 3d, so they'll fill 4s before they fill 3d. And so actually the way that the periodic table is oriented, ranging from left to right, like how we read, we don't have to memorize this trend. We get to actually use our periodic table as a tool. So to think about what's happening with our electron interactions, we have to go back to physics. And remember, when we have like charges, we're going to get repelling. And that corresponds to a positive energy level. And as they get further apart, their energy is going to go down. For opposite charges, their potential energy is negative, and that is a more stable, satisfied energy. And as they get closer together, we get more negative, so more stable, right, until they eventually touch. So the energy relationship is going to be equal to 1 over 4 pi epsilon naught. You don't need to know this. This is just some kind of constant, times charge of one of the particles times the charge of the other one, divided by the radius. This is an important equation. We're going to see it a lot. It's not going away. And so basically, as our charges get bigger or our radius gets smaller, this energy is going to get bigger. And so if we have two like charges, the Q's will be the same sign. So we'll have it be positive value. So that corresponds to what we talked about earlier. And if we have opposite charges, the energy will be negative. So that is a case where it is stable. So as we get further and further away from the nucleus, right, that our electrons do, there's a bigger radius, so we're not going to be experiencing as much of a force. We call that shielding. So the electron is shielded from the nucleus, not only because it's further away, but because the electrons are kind of blocking the charge. Each electron doesn't feel that full attraction. It's kind of blocked off by our inner electrons, shielding it. So the total force that the electrons on the outside are going to feel is called effective nuclear charge, or Z effective. That should be an E. And this is a concept that's going to explain a lot of our periodic trends. So we'll spend a lot of time studying the meaning. So hopefully the rest of the trends aren't memorization, but rather using this concept to explain. So carrying on, as we talked about, as an electron gets close to the nucleus, it feels more attraction to those protons. What also impacts is what type of orbital the electron is in. When we have s orbitals, they actually shield better than p orbitals. That has to do with there being less amount of nodes. So in this picture, we can see here's our nucleus. It has a +3 charge, so that would be lithium. Inside here are our core electrons in our 1s orbital. So they're shielding that nucleus pretty well. Since there are two negative charges out here, those are going to cancel out two of the positive charges inside for this outer electron. So this outer electron only experiences a +1 attraction to the nucleus. So it's not feeling it as much as each of these feel that +3 pull. Here we have an electron that got inside the inner electrons, so it has been able to penetrate, and it's going to be able to penetrate more often in p, d, or f orbitals. But if I were you, I'd really focus on shielding, as that concept is much more related to this course. So energy levels and sublevels fill from the lowest energy to the highest. So from n equals 1 to n equals 2 and so on, as well as s to p to d to f. So if we start with lithium, we're going to have to start, lithium is the third element, so it has 3 electrons. So its first electrons are going to be in the 1s. And we only have one s orbital, because m sub l for an s orbital has only one value. And there's 2 electrons that can fit in it. Then the next possible energy level is the 2s. And then we can fit one of those electrons in there, since there's 3 total. So those 2 plus that 1 equals the 3. So how we would draw the orbital diagram for that is we'd have a 1s orbital and then a 2s orbital. We'll fit 1s up and down till it's full, and then our 2s will do spin up. The guiding kind of principle is that we fill spin up first and then come in with spin down. When orbitals are in the same sublevel, so all of the p orbitals, right, m sub l of -1, 0, and +1, they are the same energy level. They're just facing different directions. So we would say that those energy levels are degenerate or same. And then also we can only put 2 electrons in any given orbital. That's due to that Pauli exclusion principle that we talked about earlier, with also being that the quantum numbers have to be unique to every electron. So when we fill orbitals that are in the same sublevel, so all the p's are, for example, like that, we're going to place 1 electron in each orbital, spin up, before we come in and pair things. So for example, we have carbon. Carbon has 6 electrons. So we'll have 1s, where we can fit 2. Then 2s, we can fit 2 electrons in an s orbital. Now we open up to the 2p. And so we have 2 electrons, 4 total, so we need 2 more, so we'll have 2p. So how we write the orbital diagram is, here's our 1s, here's our 2s, and here's our 3p orbitals. So 1s, 2s, 2p. So we'll fill our 1s up and down, so that's done. 2s squared, done. Now for 2p, we're going to fill up and up. So that's what Hund's rule says, is that we fill all the orbitals with the same energy first, and then we come back and fill in our pairs. So with oxygen, it's 1s2, 2s2, 2p4. So that will look very similar as far as the orbitals we draw for the configuration. 1s, 2s, 2p. So we'll have 1s2, 2s2, 2p4. We go spin up, spin up, spin up, and then spin down. That's following Hund's rule. So a summary on how to fill up our orbitals. Electrons are going to start by occupying the lowest energy orbitals before filling the higher energy. This is technically the order, although your periodic table, if you follow it, it will tell you the order. Every orbital can hold 2 electrons, and they're going to have opposite spin. This is telling us that every electron will have its unique set of quantum numbers. And then when we have similar energy level available, so for example, our p orbitals are degenerate energy, then we're going to place all of them spin up before coming in and doing spin down. So we're going to write the electron configuration of each element here. So we have magnesium. Now magnesium is in the second column of the third row. So it has 1s2, 2s2, 2p6, and then 3s2. So third row of that second column. For B, phosphorus, it's on the same row as magnesium. 1s2, 2s2, 2p6. Now this one goes 3s2, now 3p3. So it's on the third column of that P group. Bromine, we keep going. It's even further down. Have 1s2, 2s2, 2p6, 3s2, 3p6. It does go down to the 4s. So now we're on the fourth level. So that's 4s2. Now the difference is, now this is where our d orbitals catch up. So D lags behind. So we're going to have 3D, and we go all the way through, and there's 10 electrons in that level, and then 4p5. Okay, aluminum is going to be, it's on the third row, 1s2, 2s2, 2p6, 3s2, and then it's that first one in that p orbital, 3p1. So you'll see where we hit our last p, where we have a full p shell, and if there's any additional, we could actually write our shorthand. So I could actually write this as, if we look at whoever filled up our last p orbital, that was neon. So I could actually write this one as neon in brackets, saying all of those inner ones, all those ones before were from neon, and then I would have 3s2. So that's the shorthand, our abbreviated notation. Chlorine, I'm just going to pause here. I want you to pause, try these ones on your own. When you start the video, it'll have all of them displayed in about 5 seconds. Okay, so now we can see chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Silicon is the same, but it ends with 3p2. Strontium goes up through 3p6. Then we get 4s2, 3d10. So remember, it lags behind. 4p6, and then we go to the fifth row, 5s2. For osmium, I'm going to do the shorthand. It's very, very long. The long version is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, then 5s2, 4d10, 5p6. Then we get into 6s2, then we get into 4f14, so F lags behind quite a bit, behind the S and P block, and then 5d6. So I want you to do the electron configuration and then orbital diagram for sulfur, and then you'll determine how many unpaired electrons, and you'll do the same thing for argon. So starting with the electron configuration for sulfur, we go 1s2, 2s2, 2p6, 3s2, 3p4. It's in that fourth row. So when we draw those electron configurations, 1s, 2s, 2p, 3s, 3p. Label. We'll draw 1s squared, 2s squared, 2p6. Notice I'm filling them up and then coming down and filling them. 3s up and down, and then 3p we go up, 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 before we fill in the fourth one down. So 2 unpaired electrons. For argon, it's on the same column. So we go, we have 1s2, 2s2, 2p6, 3s2, and then 3p6. So if we label them, will have spin up, 2s2, 2p6, 3s2, and then 3p6. So argon, which is a noble gas we'll talk about later, has 0 unpaired electrons because all of the orbitals are filled. So as I was mentioning before, electrons in the lower energy shells, these are our core or inner electrons. And they're basically like locked in there. The ones in the highest principal energy level are our valence electrons. So these are in the outermost energy level. So for silicon, here's our electron configuration. These ones here are our core electrons. Notice 2p6, that's where we run at the end of a row on a periodic table. And then these are all on the most outer or the lowest row, and these are our valence electrons. And so our valence electrons are actually the biggest indicator of how an atom is going to behave chemically and physically. So we will be thinking about how many valence electrons elements have to figure out kind of how are they going to turn into ions and how are they going to react and form bonds. So that's how they form their bonds. So here we have, in this case, I just drew it. Our blue orbitals here are valence shell. Those are kind of locked in. They're not going anywhere. It takes a lot of energy to remove them. And then our outer ones here are the valence shell. So we're going to write the valence or the electron configuration for germanium, Ge, and then identify the valence electrons and the core electrons. So germanium is in the p block. So its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p2. So where it is in its highest shell is here. So we have 4 valence electrons, 2 from the p and 2 from the s, and then our core electrons are in this third level, energy level shell. For phosphorus, we have 1s2, 2s2, 2p6, 3s2, 3p3. So again, here are our core ones. Go to the last full p orbital, and then our higher energy level shell, our 3 energy level will be that. So we have 2 plus 3, so 5 valence electrons. The periodic table is very conveniently grouped in another way, if you didn't notice already, as our different energy levels and orbital types. So in this blue area, these are our s elements. Now notice there's a little block here where helium really should fit as far as being in the s block. But because it really has a lot of similar properties to noble gases, as it has a full shell, it is listed over here, but it really is still in the s block. Then this pink area is our p block elements. So the row number of our main group elements is going to be the highest quantum number, the highest principal quantum number, and then the column of our main group elements, so whether it's 1A, 2A, 3A, 4A, or whatever, tells us how many valence electrons. So that only works for our main group, so the S and P blocks. Then we get into D blocks. So as we mentioned earlier, the D block lags behind our S and P as far as group numbers go. So the first one up here, even though it's in the 4th row, it's actually 3D. And then we don't get our lanthanides until all the way down here. And the first lanthanide, our first F block, is a 4F. So we're all the way down in the 6S, Then we get a 5D, and then we get 4F. So kind of confusing and annoying, but that is how that works. For these elements, I want you to use the noble gas configuration for these electron configurations. So basically, find the last noble gas and then write it down, and then write the valence electrons after that, or the rest of the electrons. So for selenium, the last noble gas, so selenium's in the N equals 4 level, and the noble gas before that, so the last one on the 3rd level, is argon. So we're going to write argon. And then we'll write the rest of the electrons. So 4s2, 3d10, and then 4p4. For bismuth, our last noble gas is xenon. So then we'll have 6s2, 4f14, 5d10, and then 6p3. For iodine, our last noble gas is krypton, Kr, then 5s2, 4d10, and then 5p6. It is 5p5. Oh, that's right. 5p for iodine. 5. Okay. So now we're going to talk a little bit about transition metals. That's our D block, and our inner transition metals, our F block. They're going to actually have a different trend than our S and P block, our main group elements. So as you've noticed, there is that splitting, right? As we get higher up in energy, the orbitals get closer and closer together. So there's a point where our 4s orbital happens before a 3d orbital happens. We have a really small energy change. What's also kind of strange is in some of these transition metals, they have irregular electron configurations. That has to do with the fact that that has to do with the fact that if their d orbital is close to either partially filling or half filling or fully filling, it would rather do that than take electrons than have their s orbitals full. So some examples of these are chromium, molybdenum, copper, and silver. And what happens is an s orbital, because it's so close to the d orbital, can jump to the d orbital to create half-filled or completely filled sublevels. So for chromium, we'd expect a 4s2 3d4, but what we get is a 4s1 in order to create a 3d5, so making that d completely half-filled. For copper, we predict 4s2 3d9, but we get 4s1 3d10. And similarly, molybdenum creates 5s1 4d5. I don't want you to worry about ruthenium. It actually does 5s1 4d7, but that's kind of a one I wouldn't expect. You can see it down here. And then palladium has 5s2, we'd expect 4d8, but it really does nothing in the 5s0, we wouldn't even write it, and then 4d10. So using this, notice that when we are doing elements in the F block, we have one element in the D block, then we go down to the F block, then we come back up, do the rest of the D block, and then we hit the P block. Honestly, very annoying, but it's fine. We will deal with it. And so using that notation, we want to find out what is the electron configuration for cerium. So number 58. So notice it's right after we have our S block, so we'll have that 6s2. So that can't be it. We can't have 6s4. Then we're going to have 5 5D1. So, because we only have one element before we drop down to the F block. So 5D1. Oh, we don't have 6D1. 5D1. So far those are good. And then we have which F level? We're behind the D block. So we're at 6S. 5D, so we'll be at 4F1. Lithium, Lu, number 71. So that is over here at the end. It's going to be very similar. 6S2, so not that one. And then it will be 5D1. So that one will go first, 5D1. Oh, but it can't be 6D1, it has to go down one. And then it will be the rest of the F. To write the condensed electron configuration for lead, which is 82, it's over in the P block. We're going to have our last noble gas is xenon. Then we'll go 6S2. We will say, since we go past the D block, we're going to write all of the D block, or all of the F block first. 4F14, and then 5D10, and then 6P2, since we're a 2 in from the P block. Tungsten, number 79, that one's going to be a little different because first of all, we're going to get xenon still. It'll have 6S2. Then we're going to be, so it's 9 over, so we'll get all of since we go through all of the F block, we'll write those first, 4F14, and then we'll have 5D9. And then what this ends up actually turning to, since this is so close that this 6S2 goes to 6S1, and then we'll get 4F14, and then 5D10, which I can't write. 5D10 to fill that D block. Like we said earlier, elements in a certain column or family are going to have similar properties. And so we're going to talk about some of those. And this has to do with the fact that they have the same number of valence electrons as we go down a column. So they're going to have those periodic patterns. So noble gases have 8 valence electrons, except for helium, which has 2, but it is full because on its level, or its principal energy level, is full. They are very non-reactive, basically inert, because they have a very full, stable electron configuration. They have a full valence shell, and so they basically are like the goal for all elements. Everything kind of wants to strive to be like these and have that full valence shell. So metals make up most of the periodic table. Alkali metals are that first group, and they have 1 extra electron than a previous noble gas. So these alkali metals like to lose 1 electron in order to form a positive 1 anion or a cation, which would give them the same valence shell or electron configuration as a noble gas. Alkaline earth is the 2A, like mentioned here, and they have 2 more electrons than their last noble gas in that second column. They like to lose 2 electrons to form a positive 2 cation, giving them the same electron configuration as a noble gas. Transition metals and intertransition metals are that F and D block area. We'll say D, but they also are the F block for the inner. They have a variety of possible ions they can form, but they're mostly going to lose electrons from S, and then they'll lose it from the d orbitals to form their cations. P-block metals, so those are the ones to the left of the metalloid little zigzag staircase, and they'll lose electrons from their S and P orbitals to form cations. Metalloids are on the P block in the little zigzag staircase, and they can have metallic and non-metallic behavior, so they could either lose electrons from their P and S orbitals or gain electrons to their P orbitals to form some anions, so they can do both. So here's that again. We can see our metals in this tan color, metalloids in purple, and then non-metals in the green color. Non-metals are in the upper right-hand side of the periodic table. They tend to gain electrons in order to be like their last noble gas, so they form anions. Halogens are in the 7A, so they're one row away from. They need to gain one electron to form a noble gas. So they are the They're nonmetals. They tend to form exist as diatomic molecules. So F2, Cl2, Br2, I2 in nature. We also have the other diatomics are hydrogen, H2, nitrogen, N2, and oxygen, O2. You will need to know that. Like I said, they have one fewer electron than their next noble gas, and so they tend to gain an electron to form a -1 charge. And when they can also react with other nonmetals to share electrons and form molecular compounds. So the last thing we're going to talk about is how we can use the periodic table to predict how many or what the charge of an ion should be. So like I said, metals are going to lose electrons to form a positive charge. So our group 1 here, our alkali metals, they have one extra electron, so they're going to lose it. So they're only going to form +1 cations. Alkaline earth metals have 2 valence electrons, and they'll lose both of them to form a +2 cation. Like we said earlier, transition metals can do a variety of charges, which makes them hard to predict, but that's okay. Halogens like to gain 1 electron, so they form -1 anions. And then other nonmetals can follow a similar trend. So see this group with oxygen forms -2, nitrogen forms -3, and so on. So now we're going to try to predict the charges of these ions that get formed by the elements. So we want to look at how many valence electrons they have, and if they're metals, they're going to lose their electrons to form cations. If they're nonmetals, they're going to gain electrons. So if I look at aluminum, it has an S2P1 configuration. So it's a metal. It has 3 valence electrons. So it's going to lose all 3 to form aluminum 3+. Now sulfur is a nonmetal. It's in the 6th row. So it is 2 away from, if it gained 2 electrons, it would be like a noble gas. So if it's going to gain 2 electrons, it's going to be 2-. Nitrogen is a nonmetal, and it is 3 away from being like a noble gas. So it'll gain 3 electrons to form N3-. Rubidium is a alkali metal. It's in the first column. And it would like to lose 1 electron to form rubidium +1.